All right, well, welcome to the last day of Trig. So we've got one more topic that we need to talk about. And so that's what we'll do today. We'll talk about that, and then with the remaining time, we'll um, talk about the exam, the final exam next week. But before I go into that, are there any questions about the homework? Anything from what you've been working on? Any questions from the last couple of classes? Okay, well, hearing none, then I'm going to assume that things are going pretty well. So just want to remind you, last time we looked at vectors, and vectors are just things that we use when we want to have um, not just a number, but a number with a direction. And so we saw that you just draw arrows that point in the direction. The length of the arrow is the quantity, the magnitude. So it's how much we have. And we saw how we could add and subtract and scalar multiply. And then I showed you the dot product, which is one of the many kinds of multiplication. And I told you you'd learn about the cross product next year when you're in calculus. So anyway, the vectors are just yet another thing that uses trig. It's kind of hidden sometimes, but it's definitely there. All right, so today what we're going to talk about are what we call parametric equations. And this one's not specifically trig. Like, you can have plenty of parametric equations that don't involve trig whatsoever, but it really is kind of under the same umbrella of looking at things we already know, but in a different way, right? And that's kind of been a lot of what we've been doing here lately. The polar coordinates, right? We're looking at the plane in a different way. The complex numbers in polar form, stuff like that. Anyway, so parametric. So I'm going to start with just this question. I'm going to go to the board. So let me just do this real quick. All right, now I'm going to draw on the board a path that a plane is going to take. All right, so let's say we're looking on our map, and we're looking at where the plane is flying. So let's say the plane leaves here and travels this path. Now I'm going to draw another plane. So this airplane starts at, let's say, up at this point, and then does that path. So let's assume that they're flying at the same altitude. So they're exactly the same spot up in the air. My question to you is, are the planes going to crash? So what do you think? Yes or no? All right, so like Ariz's answer is good. Depends. Okay, so Adam just said timing, right? And I think that actually is probably the best answer to it is, well, we don't know. It does depend. It is possible that they crash. But if they were to crash, we need them to be at the same point at the same time, right? So just drawing these curves isn't enough to answer that question, right? Are they going to crash? Maybe. That's the best I could say right now. Is it possible they crash? Yep. Because their paths intersect, right? If I drew a third one, let me draw a blue one here. So let's say there's a blue path, and we'll make it easy. Just make it a line. And if you were to ask me, is the black plane going to crash with the blue plane? That one I can definitely answer no. No way. Their paths don't cross, so they would never crash. But blue and red, maybe. And it does all come back to, as Adam said, timing. When are they at those places? Well, that's what parametric equations are going to do for us. they're going to tell us not only where we're located, but when we're located at those places. All right, so anytime you want to know not just coordinates, but you want to know how they're determined by something else, we use what we call parametric equations. All right, so let me show you how these things work. They're pretty straightforward, and they really are sets of equations. We're always going to see at least two, depending upon what kind of world we're in. Like if it's a two-dimensional world, we're going to have two of them. If we're doing something in 3D, we would need three, and so on. And so what we're going to do is we're actually going to define x and y as functions of, in this case, I put t, which would be time, but it could be anything. If we want to know where things are in terms of the distance they've traveled, well, that would be a different parameter, but we could still use a parametric equation. Okay, so this is how parametric equations work. There's going to be some sort of a formula that describes the x coordinate, and then there's going to be some sort of formula that describes the y coordinate in terms of this other variable. Okay, so this guy t is called a parameter. And it's kind of the important value. Okay, the value of t is going to determine everything. But basically, we're just allowing ourselves to look at these coordinates in terms of yet another thing. And it's usually time. I'm not going to lie. It's one of the most common parameters we use. But it's not the only one. When you get to calculus, you'll see how we parameterize with arc length, so path of the curve. So basically, you'd be saying, instead of saying, where are we after a certain amount of time, you could say, where are we after we've traveled a certain distance, right? And so pretty much however you can get that set up, we can use parametric equations. So let me give you an example. It's not that exciting a one, but let's just go with x equals t plus 1 and y equals, let's say, negative square root of t. So there you go. There's a set of parametric equations. It defines a curve. There is a path that this describes. But not only does it describe the path, but it tells us when we're at points on that path. So to explore this a bit, let's actually plot some points. So let's see if we can kind of draw a graph of where we are at various times if we use this set of parametric equations. I'll move this up a little bit. Okay, so I'm going to go ahead and just put some tick marks on here so that we've got some reference points. And the easiest way to do this is actually to create your good old t-chart. Except this isn't going to be a t-chart. Now it's going to be a pie chart. Okay, but not a pie chart with the circle and all that. Not a PIE pie chart, a PI chart. All right, see the pie? Get it? Yeah, dad joke, I apologize. All right, so here's what we're gonna do. We're gonna have three columns. There's gonna be T, X, and Y. So we're gonna specify a T value. We're gonna plug that in, and we're gonna see what that gives us in terms of X and Y. So let's start with T0. So we're gonna start the clock. Where are we the moment we begin? Well, if we plug 0 in, you'll see that X becomes 0 plus 1, which is 1. And then y is negative square root of t. Well, square root of 0 is 0. Make it negative. No, it's still 0. So on the graph, I'm going to plot the point 1, 0. So this spot right here, that's where we are at time 0. All right, well, let's move forward in time. Let's say we go to time 1. Okay, well, plug that in. We're going to get x equals 2. Y is going to be the negative square root of 1. Well, the square root of 1 is 1. Make it negative. So it's negative 1. All right, so a little bit into the future, this path now brings us to 2, negative 1. And we can keep going. So for example, let's put in time 2 equals 2. Then x is going to be 3 and y is going to be negative square root of 2. So the square root of 2 is around 1.4. So we're going to be at 2, negative 1.4, something like that. And you can plug in 3, and you can plug in 4, and you can plug in 5, and you keep getting a series of points. I'm just going to do 2 more. Let's do 3 and 4. So the x is going to be 4. This will be negative square root of 3. When I plug in 4, x is 5, and y is negative 2. So we're going to get 4 and negative 3, 5 and negative 2. And at this point, we can just kind of connect the dots. And it looks like this is the path. So not only do we know the path, I just drew the path, but I also know when we're at these different locations. So if you go back to that first question I asked when I drew 2 graphs, 2 curves, and I said these are, paths of planes, are they going to crash? What we'd really be looking for is those points of intersection. Are those two there at the same t value? Okay, so that's how parametric equations are going to let us solve those kind of questions. All right, so just plotting them is actually this easy. All you got to do is plot the points and connect the dots. And in a real situation, like a real world situation, you'll have an idea of what kind of t values to use. I mean, I just started at 0 because it seems natural to start at 0. But it could have been, you know what, I don't use this set of equations until we get to t equals 10. Okay, well then I would have started with 10 and made my graph begin there. Okay, so there's usually a context to which t values to plug in. But without the context, you usually start with 0. But there's nothing to say you can't go negative. This one specifically, you can't go negative because we'd be putting a negative into a square root and then we get a complex number. But in general, you can do whatever you want. So let me show you how you can set these things up on something like Desmos. So I'm a big fan of using Desmos to help graph. So let me show you the way that you type in a parametric in there. So let me share my screen. All right, so you should be able to see my screen, which, oh, there it is. I was about to say it looks a little bit blank, but no, it's not. All right, so I got a couple of curves on here, and let me show you how we represent those things. Okay, so for example, here's this first one. You notice how it says I've got an ordered pair, got parentheses, so there's the comma. And what I've done, like this one, it says 25t This one says minus 16t squared plus 12. This would be the parametric equations. X equals 25t and y equals minus 16t squared plus 12. Also on here, you can adjust your t values. So like right now, this is going from 0 to 2. And if you look over here, you can see on the graph, going all the way from 0 to 2. 2 is going to carry on down somewhere beyond the edge of this. But there's our 0 to 2 right now. Let me show you, let me adjust the t's. So instead of 0 to 2, let's go say 0 to 1. And you notice that now it's shortened. So on this path, this is where we would be at 0. We'd be up at the y-axis here. And then at t equals 1, we'd be down at this point. That's a little bit below the y-axis. So if I wanted to put in the one that we just drew, okay, well, we'll see how this compares to the graph that we produced. We saw that the x was equal to t plus 1. Okay, so we got our t plus 1. And then the y was the negative square root of t. Right now it's got t from 0 to 1. So you notice that it's itty bitty teeny tiny. Let me make it a little bit bigger. Let's go to at least 5 because we did 0 to 4. All right, but there's our graph for our t values 0 to 5. If I zoom in a little bit. Yeah, it's not looking too different than what we drew. And obviously, if I had gone further in my t values, I could have seen more and all that. But there it is. All right, so you can have all kinds of fun with these, and you can plot all kinds of crazy, weird stuff. Like, since this is trig class, how about we put in some sines and cosines and stuff like that? So how about we do sine of t for our x? So this will be x equals sine of t. And how about we do y equals cosine of t? Let me turn off this other one. So here is a graph for our t values from 0 to 1. Well, let me make that a little bit bigger. Like, how about we go to 5 again? Huh. Wait a minute. That's starting to look like a shape we know. Kind of looking like a circle, right? Notice what happened when we went from 0 to 1. I had just a little portion of it. Then I went 0 to 5, and I got this bigger portion of it. Well, let's make that even bigger yet. Let's go to 10. Huh. I got a whole circle. Well, you shouldn't be too fooled by that, because if you think about it, this is sort of how we defined the unit circle, right? The unit circle, let me actually make the unit circle that you know and love. It was x was equal to cosine, and y was equal to sine. And let me just show you what happens as we increase the angle. So I'm going to go from 0 to pi over 4. And notice what it did was it gave me the circle that goes from an angle of 0 up to pi over 4. If I change that to a 2, now we've gone to pi over 2. If I change it to just pi, we're halfway there. And so on and so forth. So like I could do something like 4 pi over 3. Well, that was the angle 4 pi over 3, and so on. So you start throwing trig in there, and you start getting a lot of this circularness. And that's not coincidence. That's because that's how we defined the unit circle. So in fact, every time you did anything with angles, you were parameterizing. Right? As soon as you said, let's let x be something about the angle, or y be something of the angle now is your parameter. So instead of t, this isn't really so much a where are we after a given amount of time. This would be where are we after rotating through a specific angle. All right, well, anyway, so there's a circle. I'll just go to 2 pi and now you can see the whole circle. But you can get all kinds of fun stuff. Like, let's try this. I'm just randomly putting stuff in now. So how about we go cosine of 3t, comma, 2 sine of 5t. Let me turn off the circle. And so you look at that and you go, all right, well, whatever. Let me increase it a bit to say pi. Oh, that's definitely more interesting. How about we go to 2 pi? Whoa, that's way more interesting. Let's go a little bit further, see if anything changes. We'll go to 4 pi. Oh, there it is. There's that picture. So this one has a kind of crazy path, right? You'll notice that there's just all this kind of going up and down and back and forth. But this is the set of parametric equations that we would use to describe it. All right, so before we go too much further, I want to give you some like why. Why do we actually care about parametrics? I mean, other than our plane's going to actually collide. Well, we use these when we're describing motion. If you end up going down the physics engineering path, that's what a lot of that is talking about motion and describing where things are. And the motion of particles is complicated. Not just particles. You want to like explain the motion of the Earth. Now, most of you, if I asked you, in fact, I'll ask you right now. So the Earth goes around the sun. We're pretty sure about this, right? So the Earth goes around the sun. What path does it take as it goes around the sun? So quiz for class. Okay, so Adam says ellipse with a question mark. Mariola backs that up. Nobody wants to say circle? Okay, good, because it's definitely not a circle. And you were probably taught somewhere, possibly even in 103B, the class before this, that the Earth goes around the sun in an elliptical path. Okay, so is it actually an ellipse? Now, I like how Adam just put in an ellipse that's kind of spiraling through the universe. Let's just hold off on that for a second. You're kind of jumping the gun, but let's just say we're going to go with it's an ellipse. That's not true. I'm actually going to stop sharing here so you can see me. I'm going to start making hand gestures. So. All right, so it's technically not an ellipse. It's mostly an ellipse. But if you actually were to look at it, and we're not talking about the spiraling through the universe thing yet, but there's like a bit of a wobble as we're going around in this ellipse. And that's because of the dance, the gravity dance, right? So all the objects in the universe have a gravitational attraction to every other object, right? Like right now, I am pulling on you gravitationally. You feel it? I hope not, because it's super small. It's super small because the gravitational force is based on the mass of the objects and how far apart they are. You and I are not very massive, and we're super far apart, right? I don't know who's closest to me, but we're all like far away. Even if we were in the classroom together, that distance, if we're going to practice social distancing and be 6 feet away, that 2 meters, because of our sizes, our small sizes,
the force that we would calculate is so minute that there's no way we would feel it. But when we get big things like the Earth, the sun, the planets, the moon, right? These kinds of things, those forces are noticeable. And what ends up happening as the Earth's going around the sun is it's not purely an ellipse, but there's, kind of like a little wobble. So if you wanted to actually describe the Earth's position relative to the sun, it's a very complicated formula. It's a very complicated equation, but it can be made much easier if we parameterize. Okay, but now let's throw in what Adam just said, right? Technically, it's spiraling through the universe. Well, the sun itself is also moving. It's orbiting the center of the galaxy. So we're in the Milky Way galaxy, and in the center of the Milky Way galaxy, there's a black hole that's exerting a gravitational attraction to all of the stars and everything else that's in the galaxy. And so that's going on. So now think about this. We're going on an ellipse, a wobbly ellipse, that's going around the sun that's also going in a bigger ellipse, well, bigger wobbly ellipse. And the next thing you know, oh my gosh, it is such a crazy, weird equation that if we tried to do it in just x's and y's without a parameter, we'd be screwed. All right, so there are lots of uses of parametric equations, lots. And in fact, vectors, in a way, are parametric equations. Think about when we were describing vectors, and I said that one of the easiest ways to do it is to break it into the components, the x components and the y components. Well, we're setting x equals and y equals, so we're parameterizing. So specifically in physics, you will see parametric equations a lot. We'll also deal with them in calculus, see how we can actually do calculus on parametric equations, which I think calculus is really a tool to do science. So in order to do that physics, you need to know parametrics. All right, well, along those lines, let's actually do a physics example. But this will be an easy one, super easy one. All we're gonna do is throw a baseball. And we're gonna even make things a little bit easier. We're going to assume that there isn't air resistance. So maybe we're actually throwing a baseball on the moon where there is no atmosphere or something like that. Okay, so let me show you what that would look like parametrically. And we'll see how we can then use that to determine the actual path and such and so forth and whatnot and blah, blah. All right, so let me go back to the board.
All right, so I'm not going to get too heavy into the science because this is not physics class, but I do want to share with you just sort of the basics of what's going on. So if we were to throw a baseball, okay, so we got our baseball and we're going to toss it here. You probably have learned that it's going to follow a parabolic path. This is one of those things that we teach you and we use as a justification for worrying about quadratics and parabolas. But you were taught it's going to follow a parabolic path. I'll show you why. I'll show you where that comes from using the idea of parametrics. All right, now, here's what we're going to do. We're going to think of this motion as two parts, having two parts. There's the, what about going away from us? And then what about the dropping? Because those are independent. They really are. Because if we're assuming there is no air resistance, the part going forward isn't going to change. When I throw the ball, it's going to have a certain velocity, a certain speed, and it's not going to be affected by anything. So we can use that same velocity the entire time. The up-down, though, is going to be affected not just by how I threw the ball, right? If I throw the ball upward, obviously I'm affecting where it is up and down, or if I throw it downward. But regardless, gravity is also affecting it. Because I could even throw it straight. If I threw it straight, the ball doesn't continue to go straight. Every one of us knows this. It's going to fall into the ground, and that's due to gravity. So what we can do here is actually create a set of parametric equations for the path. All right, now I'm going to be kind of generic. No, let me give you a specific. So what I'm going to put here for my x, I'm going to let x equal 25t. Now, what this is saying is that I'm throwing it with an initial speed of 25 meters per second. Okay, so this is coming, we're throwing it straight out at 25 meters per second. And that's why we have 25t. So every second that goes on, this ball goes another 25 meters. That's really fast, by the way. All right, so that's 25 times t. So in 4 seconds, it's gone 100 meters. 2 seconds, it's gone 50 meters, and so on. All right, now the y, since I threw it straight out, there's not going to be anything due to that 25 meters per second. None of that speed is actually pointing in the y, so we're not going to have anything there. But there is going to be gravity. Well, you're just going to have to take my word for the number. But it's going to be minus 4.9 t squared. Some of you may have learned gravitational numbers on Earth, and in metric it's 9.8 meters per second. And the fact that this is half of it is not coincidence. But the t squared, really where that comes from calculus. So next quarter in Math 105, you'll learn about that. Okay, so y is going to be minus 4.9 t squared. And then I'm also going to put a plus here, which is going to correspond to how high up we were when we threw it. So let's say that we're doing this from the top of the parking garage over at like Montbleu or something, so we can have some height of some type. Let's say we're 10 meters above the ground, so we'll just do plus 10. So this would be a set of parametric equations for throwing a ball straight out. I'll talk about what happens if we go at a different angle in a second. All right, so here's our set of parametric equations, and if we wanted to graph it, we could plug in t values, get their corresponding x's and y's, plot the points, and see what happens. So let me again real quickly share my screen. So we'll go look at Desmos. We'll plot this, and I will help convince you that it does need to be a parabola. All right, so it's pretty much what I have drawn up here. Except let me change the numbers here. So we had 25t, that was our x. Our y was 4.9 minus 4.9 t squared, and then plus, what was it, 10? Okay. And let me turn it on. Right now the t values are from 0 to 1. You don't see anything, so let me zoom out. Oh, hey, look, there's some graph. So notice that it started 10 meters up. We threw it, it starts going out and starts dropping. Well, this only goes for 1 second. So if we wanted to know where this was, we could plug 1 into this equation, and you would see that x is 25, and then y is 5.1. And so that's that point right there. Let me extend the t. So now we're going from 0 to 2. So notice that the x's now we go out to 50. Well, let me go really far out. We'll go to 20. And let me zoom out a bit. Sorry about that, guys. It's my phone. I'm going to turn that off. But if you look at this, you can actually see the parabola, right? So this thing is following a parabolic path. Now, in terms of real life, we're never going to get this part because this would be negative elevations. I mean, I guess we could have that if we were, say, in Death Valley. We could go down a little bit, or if we're by the Dead Sea or something like that. There are a couple places where we can get below sea level. But in general, we'd be trapped to this part that's above the axis. All right, well, it's definitely a parabola. But I want to convince you that algebraically. So here's what we're going to do. We're going to do what's called eliminating the parameter. And it's exactly what it sounds like. We are going to get rid of the t. We're going to get rid of the t, which then is going to make this be in good old rectangular coordinates, just x's and y's, and we can see what that graph would be. So basically what we want to do is you want to solve one of the equations, either the x or the y, it's your call, for t. And then what we're going to do, we're going to plug this into the other equation. And what that's going to allow us to do is have no more t's. So it's kind of like when you do solving systems of equations, because we have two equations. It's just since we have three variables, we're only going to be able to get rid of one. All right, well, let me show you how this works for this guy. So we have a choice of solving either the first one or the second one for t. And the first one is the one that you should pick because it's going to be pretty easy, right? If I solve that for t, I get t equals x over 25. And then I can fire that into the other equation for t. So what this would look like is y equals negative 4.9 times x over 25 squared plus 10. Well, let's just see what that does for us. So we have to square both the x and the 25. So we get y equals negative 4.9 x squared over 625 plus 10. And at this point, we could use our calculator to go ahead and figure out what that number is. I'm frantically trying to find my calculator. It's not handy. Oh, there it is. Okay, so if we take 4.9 and divide it by 625, I get 0.00784. So we have y equals negative 0.00784 x squared plus 10. So let me put a circle around that. And so there is the equation in rectangular, in the way that we are used to seeing them. That's the equation of the path that baseball is following. So notice that it is an x squared, so it's a parabola. It's a negative, so it's a sad parabola, which means it's going to be a frown. its vertex is up at 0, 10. And so it completely matches what we saw. Okay, but I do want to mention this. If you were to say that the ball follows this path, that's not quite entirely true, because it only follows part of this path. And the part of the path that it follows is when x was greater than or equal to 0. Because if we're talking about this as t is time, negative time doesn't make sense. The ball isn't going through the air before I threw it, right? It has to be from 0 on. So eliminating the parameter is really useful, but we do have to be careful that we don't necessarily get the entirety of the graph, right? We can only get part of it, like in this case. So I want to show you a couple more eliminating the parameter, because it's kind of a useful thing. And sometimes we have to play different tricks. Okay, so how about I give you this one? Actually, before I go there, any questions on this example? So let's try this. Let's do a different one where we've got x equals 2 cosine t and y equals 3 sine t. Okay, but I want to eliminate the parameter. I want to figure out what the rectangular form of this equation is, because then maybe we can recognize it, see what the path looks like, without having to try to plot points in this weird, unfamiliar world. All right, so think about what I said we wanted to do. We want to solve one of the equations for t and then plug it into the other. All right, so pick one. Which one do you want to solve for, the x or the y? So Amber suggested x. Was there a reason, or just because it was the first one? Okay, just because we did it last time. So then Era says, does it matter? Well, does it matter? No, you can always solve either equation for t and put it into the other. But sometimes one is easier than the other, right? Like the example we just did, it was much easier to solve for t in the x than in the y. But for this one, I would say it's pretty much same, whether you solve it for x or you solve the y. So since we did x last time, let's solve it in y, just so you can see it doesn't really matter. All right, so let's take this second one and solve it for t. So if we take that and we solve it for t, we're going to get y over 3 is equal to sine of t. So t is going to be sine inverse of y over 3. And now we'll take this and we'll put it into the first equation for t. So what we've got is x is equal to 2 cosine of sine inverse of y over 3. All right, we just eliminated the parameter. So what does this look like? Anybody recognize that graph? If you could only see my internal thoughts, I had a really big smirk as I asked that question. Because of course not. I don't know what that looks like. But you may recall we did things like this before. Remember when we did mixed composition of these inverse trig functions? You don't have to remember how. I'm just asking you remember that we did it. Well, this is one of the reasons why we showed you how to do that before, so that when we run into something like this, we can actually turn it into just an algebraic thing and not a trig expression. So let's do this the old right triangle way. So what we've got is some theta where the sine is equal to y over 3. Okay, so sine is opposite over hypotenuse. We can use the Pythagorean theorem to find the other, and that's going to be 9 minus y squared. And what we want now is the cosine of that angle. So the cosine of that angle is going to be the square root of 9 minus y squared over 3. So if this jump is totally throwing you right now, go back and look at your notes on the how do we go about doing the mixed composition, because it definitely comes in handy here. Okay, so I'm going to ask the same question. Anybody recognize this kind of graph that is? So again, I have an internal smirk. It's not quite as big because some people might be able to recognize that. But even in this form, you still don't really know. So let's do some algebra. Mostly, let's get rid of that square root. So I'm going to start by moving the 3/2 over just to get that square root by itself. And now I'm going to square both sides. So that's going to give us 9/4 x squared equals 9 minus y squared. So same question as before. Anybody recognize that shape? Because now we're getting close. You might be able to pull this one out. Okay, so Adam just suggested hyperbola. That's really close. It's actually not a hyperbola, but really, really close. And I'm going to guess you're probably thinking the hyperbola because you see the one is positive, the other is negative. But let me remind you that when you deal with the conic sections, you want all your variables on the same side of the equation. So if I move that y squared over, they're both going to be positive. So let me just do a slight bit more algebra here for you. So I'll move the y squared over. So I have 9x squared over 4 plus y squared equals 9. So it's not a hyperbola. What is it? Good, it's an ellipse. And with the ellipse, we always have it as equals 1. So if we were to just divide everything by 9, on this first one, the 9's cancel, and you're left with x squared over 4 plus y squared over 9 equals 1. So what we started with this x equals 2 cosine t, y equals 3 sine t, is actually giving us a path that's this ellipse. It's centered at the origin, goes left and right 2, and up and down 3. So it probably wasn't really clear from the beginning. It definitely wasn't very clear when we did the first substitution, when we had the cosine of the sine inverse stuff. But now, if you know your conic sections, you can look at that and go, oh yeah, that's totally an ellipse and I can draw its path. And then we can figure out where we are on it by plugging in the respective t's and figure out exactly where on that ellipse we are, especially if we're given some sort of a restricted t interval. All right, so sometimes eliminating the parameter is a little bit brutal, but this one, turns out there's a trick. We can do this faster. Check this out. So if you ever have the trig functions, sine and cosine, I'm going to give you a suggestion. Instead of solving for t, instead solve it for sine and cosine. So here's going to be an alternative. And just to prepare you, you're going to get mad at me here in just a second. You're going to get really mad at me. Mostly because I didn't show you this first. So let's solve for the sine and the cosine. So we're going to get x over 2 is equal to cosine of t. And we have y over 3 is equal to sine of t. But now we're going to bring back our good friend, the Pythagorean identity. So Pythagorean identity, the granddaddy of them all. You probably all have it memorized by now. Remember that one? Sine squared plus cosine squared equals 1. So I already know that this is true always. Well, let's put these in for sine and cosine. So we get y over 3 squared plus x over 2 squared equals 1. And if you square, you get y squared over 9 plus x squared over 4 equals 1. And in case you didn't catch this, yeah, that's exactly the same thing we found going the other way. So yet another use of the identities. Totally random. Never would have thought about it, right? Well, this is why we have identities, and this is why it's important to get comfortable with identities and know how to deal with them, because it's going to really suck for you in an example like this, where if you don't remember the identities and how they work, you got to go that long way that I showed you first, which was a total pain. But because we have identities and well, because I'm comfortable enough to push you in this direction, but if you get to this point, you can go, oh wait, I've got cosines and sines, I can link those together. Same thing if I had tangents and secants, or any of the identities, any of them whatsoever. Right, so this can be identities can come in, can be useful in all sorts of situations that you just can't necessarily anticipate. So, but anyway, there you go. There's an ellipse. So it turns out that if you ever have a multiple of cosine and a multiple of sine, and it can be swapped, right? It doesn't necessarily have to be that the x has the cosine or the y has the sine. But if one of them's a multiple of sine and the other's a multiple of cosine, you will always get an ellipse. Always. All right, so eliminating the parameter. It's very useful. And watch out for tricks like this. All right, so any questions on that one? All right, so Adam said, if you have sine on x, do you need to figure out cosine? I don't think I quite understand that question, but let me just start with, so you say we have a sine on x. So
Well, yeah, I was wondering, like, you say if you had a cosine or a sine on x, do you just need to figure out what the triangle actually looks like and then swap it back in, or does that, it just works that way? It doesn't really matter. Like the identity works either way.
So the identity always works, no matter what. So as long as you can solve these things for the sine and the cosine, you're always going to be able to do that. So like, let me even change this a little bit. I'll just swap sine and cosine. So let's say we got 4 sine, and this other one, let's say, is 3 cosine.
Well, what if you had both sine was really more, or both cosine was more so my question?
Oh, okay. So if we had something like this.
Yeah, exactly.
Okay. So if they're both sine or both cosine, you actually are not going to get an ellipse. And if you wanted to solve this, I would do the same thing that we did before, which is solve for sine. So since it doesn't matter, I'll just use this bottom one. So we get that y over 2 is equal to sine of t. And now I would take this and plug that in to replace sine of t. I know sine of t is equal to y over 2, so I'm going to make that sine of t y over 2. So this is actually a much easier one, because we literally can replace that entire sine. And so we get x is equal to y. So this one would be the graph of a line. This is a line with a slope of 1/2. You solve it for y equals, right? You get 1/2 x. So it's a line with slope 1/2, goes through the origin. And where we are on that line is dependent upon what's going on with that sine value. So it's actually nice if they're both the same, because then you don't even really have to use the identities. So did I kind of answer your question?
Yeah, I see it.
Okay, cool. All right, well, there's your little introduction to parametric equations. Like I said, it's not really a big deal. It's just we're kind of looking at the world slightly differently, where we want to know not just where we are or how we're traveling or what path we're traveling, but we want to have a little bit more information in there. And in this context, it's what angle are we at, or what time are we on, or whatever. All right, so there's parametrics.
Well, let's take a real quick break. I actually have to go use the facilities real quick. So let me pause the recording. All right, so here we are. We're ready for the final exam. We've gone through everything here in Trig. So let's just sort of talk about what to expect and all of that. Okay, so excuse me. So first of all, in terms of the schedule for finals week and everything, so you'll notice that on the syllabus, there wasn't a day of class for next week, and that actually is correct. Okay, so we don't have class next week. We have only the final exam. And the final exam is on the 22nd, which is Monday. Okay, so instead of having any kind of class, we just have our exam Monday and we go. All right, so that's kind of good. That's sort of the, I don't know, I call it the Band-Aid kind of deal, right? We're just going to tear it off. We'll be done. So you'll take your final, and then you don't have anything else to worry about with this class for the rest of the summer. It will also then give you time to deal with your other classes and get ready. So in terms of how it's going to go, it's going to be the same kind of deal that we've been doing the whole time. which is I will have it set to turn on at 11 o'clock at the usual class time. And then you'll have your 2 hours to do it. And I'll still build in the extra time to get it submitted and everything, just in case. Okay. A couple of things regarding this. The final, you know, there have been a couple of people that have turned things in just slightly late. The final exam needs to be in on time. All right, I've got a real short time to turn things around. So Hava, I have no idea how many questions are going to be on it at all. My guess is it's going to be just slightly more. Maybe not like more number of questions, but more things because it's a final. I'll get to that in a second. So please plan accordingly. All right, when I do this, I give you that extra half hour. That's not meant to be an extra half hour to do the work. That's meant to be extra time to deal with the, oh crap, my insert favorite thing here is having trouble, right? So that if something's going to happen, then you can ask me for assistance and whatnot. I'll get to that also, William, in a second about word of the day. Actually, while we're here, word of the day for today. So our last one, and again, we're just going to go with things that I have handy. Pine tar. So it's a double word, pine tar. I'll go ahead and put it in the chat as well, just in case. All right, but it's pine tar. It's the stuff that you use for putting on baseball bats so that you get a better grip. All right, so it's also got a very distinctive smell. I love this smell, and it's definitely one of the things I'm missing by not being able to go to baseball games. I have tickets to the season tickets to the Aces, and where I sit, sometimes you get a good little whiff of the pine tar in the bat. So yeah, it just reminds me of baseball. Anyway, so there's your word of the day. But yeah, actually there will be something about word of the day on the final exam. What I'm going to tell you though is that it's going to be important that you remember what days specific words were, right? Not just the specific words, right? So just be aware. It'd be good to know the different words of the day for the various days. But okay, so the final exam in terms of structure, it's going to be pretty similar to the ones that you've done before. In terms of length, you know, like I've asked, I'd say it's going to be pretty close, maybe a little bit longer, but not like twice as long or anything like that. It also will be cumulative, meaning you need to know everything that we've covered in this course, right? All of it's fair game, even going back to day one. So day one, when we were talking about converting degrees to radians and, you know, like areas of sectors and stuff like that, all of that is fair game. Now, before you start getting too overwhelmed by that, I want you to realize that we've been building in this class. So that stuff from the very first week, we did today. We legit did today, right? So hopefully it's not as daunting as it may seem because of the fact that it really, really builds on top of each other. I'll get to that as well, Juan, in a second, in terms of practice and things to do. So again, same structure, kind of like you're used to, but just more. So something I want to make perfectly 100% clear. When you take this exam, I want to see your work. I don't want to see somebody else's. I don't care what Symbol Lab or anything else shows you. Okay, I want to see your work. I don't want these miracle jumps where you punch it into your calculator and you get this magical number or something. Okay, I don't want any of that. I want to see what you know. And if you run into something that you don't know, you run into something you don't know. It's totally fine. Okay, but I want to see your work. I will know. I will know if you're doing something that's not yours. Okay. So if that happens, as I mentioned last time, you're getting a 0 on the final, period, because it's ridiculous. Okay. So do your work, show me your steps. If you don't know how to do something, okay, own it. You don't know how to do something. It's not the end of the world. Okay. So if you're concerned and you're like, oh my God, he might think I'm, explain your steps. Okay. Explain it. Take that extra, 10 seconds to write what you did there. If you think that it's something kind of funky that I'm going to question. Okay. So it never hurts to put a little more explanation on there, but do not use something else. Use your brain to show me this stuff. Okay. Anyway, all right, so it is cumulative. Now, a couple of things that I am going to recommend for you in terms of practice. One is I'm going to show it to you in a second, screen share, but I have a kind of a standard review sheet that I produced for Trig. I had to change the dates on it for your specific class. I'm going to show it to you, but I'm also going to put it up on Canvas in the files so that you can go and you can download it and look at it. So I would use that as a good starting point. Look through that list, think about what's on it, think about what bits of it seem pretty familiar, which ones don't. That can help you concentrate on the topics that are a little bit more of an issue for you. Okay, so I would start there. The other thing I would do then is I don't have like a sample test or anything. You do have tests that I've already given you and quizzes and things like that, and you've got all the homework sets. You can go to those and practice some. Now, what I recommend that you do is that you try to practice them with no assistance whatsoever, like not your notes or book or anything. And just like, I would just write it down on a piece of paper, put everything else away, and try to do that problem. Now, the reason I suggest doing that is that often we have a incorrect assessment of how well we actually know things, right? Because you might go, oh yeah, no, I know how to do that. And you kind of like, because you keep looking at a homework problem that's similar and you're like, yeah, no, I got this. But you don't really. You have it when you've got that assistance, but you don't really know it. And so if you do this, if you just kind of put it on paper, put everything else away and try it, you'll actually have a really good sense of how well you actually know the material, right? And then that can also help you kind of figure out what to concentrate on. So speaking of, let me go ahead and share that with you and just kind of give you an overview. And like I said, I do have to adjust some things slightly because I need to change some dates and stuff like that. So to be honest, it probably will not be up on Canvas until tomorrow, because as soon as I'm done with you guys, I have class from 1 to 3 and another one from 3 to 5:30. So I'm kind of booked for the rest of the day. All right, so hopefully you can see up on the screen. So I've got a little final review. All right, so again, ignore the dates. It's from a different class many, many years ago, right? 2014. I told you I've been teaching Trig for over 20 years, so there's a lot in there. So what this starts with is just a kind of outline of the different things that we did. So we started just talking angles, right? We looked at radians versus degrees, how they're related, how they're defined. We then looked at all the special angles, right? So I gave you the ones that are in the first quadrant, because those are really the ones that matter. And then, all the rest. So real quick, something else I want to mention in here under the special angles thing. This is where reference angles came into play, the plus and minuses of the different things in the different quadrants. Okay, so all of that is kind of incorporated in that area there. So when it comes to this, things that you definitely should know how to do. You should be able to take a degree or a radian and go to the other form. Specifically, you want to be in radians. You'll notice, like, I don't know, do you remember the last time I actually did a degree thing? I used degrees when we were talking about triangles and solving triangles, because that's sort of the standard. But beyond that, I did everything in radians. Again, trying to prepare you for calculus where you want to be in radians. You really want to be in radians. Makes life a lot easier. But anyway, so know how to go between radians and degrees. Know your special angles. And know how to determine things like plus and minus for the various places, okay, because that's kind of a big deal. All right, so after we did that, we really talked about the trig functions themselves. So we define them according to the unit circle, and we also define them according to right triangles. So know about them, be able to graph them, be able to do the domain, you know, figure out domain and range and things like that. In that section on graphs, that's also where we did like curve fitting. We gave you data, and then you were able to kind of create a sine or cosine that fit it. So know things like amplitude, period, phase shift, etc. This is another place where you definitely need to show me your work. You gotta convince me that you got those points or got the graph or whatever that information is, you know, not using just some technology. All right, so make sure that you truly understand amplitude, period, phase shift, and so on. Okay, so that would be under the graphs area of that. And then we also talked about the inverse trig functions. So when I put here domain range, that's kind of the most important piece. Because when we defined them, remember, we had to restrict the angles because otherwise they weren't functions, or they weren't what the trig functions weren't one-to-one, and so there were no inverses. This bit where I put graphs, strike that. We didn't talk about the graphs of inverse functions at all, so don't worry about that. But maybe in its place, something to remember for inverse functions is composition. I mean, we did it just today when we were eliminating the parameter for that ellipse. So know how to do the composition. So when I put this up, I'll change that so it says composition. Okay, and then we talked about identities. And this was a huge part of the class. And this is a challenging part of the class, right? And it's one of those things that gets better with practice. Practice, practice, practice. But I kind of I broke them down into the big sets. We had the reciprocal. So that's the whole like tangent is 1 over cotangent kind of thing. You have the Pythagorean. I didn't put on their quotient, but the quotient that was like tangent over, or is sine over cosine. The sum and difference of angles, the double angle, power reduction, half angle, product of sum, and sum to product. So we have a lot of them there. You don't have to have them memorized, right? And obviously the way we're doing exams now, you know, having them memorized is silly. So feel free to make use of that sheet that I put up on the Canvas page. But know how to manipulate them, know how to use them, know your algebra tricks, factoring, the fraction stuff, right? All those kinds of deals. Because I will ask you to confirm some identities on the final. It will definitely happen, all right? And also in there, realize that identities can be used all sorts of places. And in fact, we saw them in some of these later things. Okay, so that was a big chunk. And then we had the big chunk that were applications. So let me move this up a little bit. So we had the angular quantities. So what I mean by that, that's like the arc length, S equals r theta, the angular velocity, That was the omega, the curvy W thing. So then the curve fitting, solving equations. Remember with equations, there's a difference between all solutions and just those in an interval. So watch out for what I'm asking for. And then we did right triangles. We also did the, what I called wrong triangles, the oblique triangles. And that's where we had law of sines and law of cosines. We now most recently have looked at vectors and imaginary numbers. And then I put on this next one, other ways to view the world. You've got polar coordinates, and I think I'm going to add on to that parametric. So parametric is just yet another way of viewing the world. All right, so that's kind of an outline of all the different things that we talked about. And probably as I went through this, some of those things you started going, oh man, I don't remember at all inverse trig functions. And that's probably good. Like this can help you sort of prioritize things that you need to go back and look at. Okay, so as I put here, obviously it's not complete. So I also made a list of a bunch of things here. So I know it says definitions. It's not like I want you to define it. All right, there's not going to be a question on there that says define a unit circle or anything like that. Mostly what I mean is if you see these words, you know what they mean. All right, so these were just the kind of things that we talked about that I didn't want to make the outline crazy, so I kind of put those here. All right, so in terms of the structure of the exam, it's going to slightly change because of the fact that we're doing this in this virtual world. But it is going to be designed to be 2 hours, similar to those of previous exams. So where I put there, it says approximately 40% will cover chapter 9. Disregard that. But about 40% of it is going to be from the stuff that we've talked about since the last exam. So I think that's actually for us chapter 10. So the last exam went through identities and then the triangles stuff. So this is going to pick up after that. So about 40% of it is going to be on polar coordinates and complex numbers and vectors and parametric equations. Okay, so roughly. The remaining 60% is going to be comprehensive. So you'll get things like solve this equation, confirm this identity, solve this triangle, you know, figure out the curve that fits this data, those kinds of questions that came from before. Okay, so that's why it's cumulative-ish. All right, but I also want to kind of highlight this little bit right here, because I think a lot of times students, their understanding of what a final is different than mine. What I'm looking for is, do you know how to do the main big things from this class? The final exam is not going to be as detailed questions as a regular exam, right? And like, think about this. The last exam you took, there were like 4 solve a triangle. And there were like 4 prove these identities and all that. I'm not going to do that. There's going to be, like let's just be real. Here are things that are definitely going to be on the exam. I am going to ask you to solve a triangle. I'd be failing as a trigonometry, triangle measurement teacher if I didn't, right? So there's going to be some sort of, here is some information about a triangle, some combination of angles and sides, solve it. Okay, there's also going to be at least 1, maybe 2, prove an identity. There's also going to be 1, possibly 2, solve an equation. There's going to be something about graphs of sine and cosine. I'm either going to have you find the equation of a graph, like if I draw one, give you a picture, you find the equation, or I'll give you an equation and you need to draw it, or I'm going to make you fit it to some data. but there's going to be a question about the graphs of sine and cosine. Now, the reason I can tell you that these are going to be on there, twofold. One, those are the important things we talked about. Those are actually really important skills to have later. Okay, so I definitely need that there. And then secondly, well, yeah, I can tell you you're going to have to solve an equation, and until you see what that equation is, you don't necessarily know what you need to do. So it's one of those, yeah, thanks, but at least you know that's kind of coming. So we're talking bigger ideas. And if at this point you're like, well, maybe I'm not really sure what those bigger ideas are, some other big ideas other than the ones I listed, radians. Radians are a big idea. So being able to just deal with radians, whether it's converting back and forth or knowing the radian values for special angles and things like that, radians are a huge thing, which you probably have already picked up that I find that very important. Again, it's important because for you in the future, you'll need it. So knowing how to deal with radians and all that. The angular quantities, specifically S equals R theta, the arc length, and how it's related to radius and angle, huge idea. The definitions of the trig functions, just how they're defined, huge. SOHCAHTOA, right? That's what I mean by definition, like SOHCAHTOA or the unit circle X's and Y's kind of thing. That's a huge idea. Solving equations, inverse trig functions, huge idea. Specifically, the restrictions on the angles. That's something that's really, really important. Inverse trig functions themselves are supremely useful because that's how we find angles. But the fact that we're restricted is a big deal. So solving equations, big idea. Manipulating identities, big idea. And then again, like solving triangles themselves, big idea. All right. So those are like the big ideas of that 60%. The 40%, the bit on chapter 10, that's going to be kind of the same level of detail that you're used to, right? So in terms of what I might ask you there, those can definitely be more varied and more detail oriented. But from the previous chapters, I'm talking big ideas, really important for going further. Because again, really my goal here, this entire quarter, my goal has been get you to a point where when you get to calculus, you're going to be able to fly through it and have no troubles because you understand the trig. Okay, so, and that's really what I'm looking for on the exam. So this last line, don't worry about that last line because you already have been supplied with a sheet of identities. And just so you know, if you were taking this test in person, I still give you a sheet because nobody needs to waste their time trying to memorize all of them. You might have some of them memorized by now, which is awesome, right? But I'll be honest, I don't have all of them memorized. The product to sum and sum to products, I don't have those off the top of my head at all. So that's not an expectation I have for you. All right, well, I'm going to stop sharing here. So there's just sort of a little recap of what we've talked about. So some other things that you can do. You can go back and go into any of the homework assignments that I've given you so far, and you can redo any of those problems. It doesn't change your score. What you have to do is you have to click on the, says something like do similar, or I don't know exactly what it says. But you can click on those and then it'll pull up one that's like the one that you already did, and you can practice them. So that would be a good thing to do once you've keyed in on some of the topics that you're having a little more trouble with. I'm sure there are all kinds of online resources to get practice for this. You know, the internet's got everything you could ever imagine. But also just be careful, because sometimes they're not correct. And so just remember, not everything on the internet is true. Sorry, spoiler alert. Anyway, and good, Hava. I'm glad that makes you feel better. Whatever that was, I'm going to guess that little talk through of what we've been doing. Anyway, so like I said, Monday, and I'll put a message on Canvas to remind everybody, but Monday, 11 o'clock. Again, same deal, 2 hours to take it, extra half hour to deal with technological issues. I will plan on being online during that time. It might be in and out. I don't know if I've told you guys, but in my life right now, things are a little bit, there's a little upheaval. I'm in the process of moving. So internet is questionable starting next week, which is a wonderful time for that to happen. But I'll make sure that I'm at least somewhere where I can check in periodically during that time. So if there are any issues or questions, you can ask them. If there are a couple of you that get like extra testing time and all that, just let me know ahead of time what times work for you. Just shoot me a message or an email, and we'll get it set up. So I think that's everything I have to say. Is there any questions you guys have? Are there any questions that you guys have that I haven't addressed, or other comments, concerns? Oh, okay, so still office hours on Friday? Yep, I will have office hours. I'll actually even have office hours during finals week. So my plan is to be on in the morning, 9:30 to 10:30 on Monday, just like I normally do. So you can still get me office hours. Tomorrow I'm gonna have to change my office hour again. I have something that's going on in the morning, but I will post that as well. But yeah, I'm still around. So you can find me at usual times. But good question, Hava. Any others? All right, well, I guess with that then, I'm going to go ahead and pause our recording.